We know more about life on Mars than we do about planet Earth. Despite our greatest technological advancements, most of our planet's biggest dumping ground, the deep ocean, remains a cosmic unknown. Imagine an entire realm that science has barely touched. Join us as we dive into the breathtaking blank spaces beneath the waves. Imagine dipping a single finger into the ocean, a casual gesture that somehow encapsulates a realm of unimaginable depth and biodiversity. The vast blue expanse is not just wet land. It is arguably the planet's largest continuous biome, covering over 71% of Earth's surface area. While our great-great-grandparents could only chart what their respective ships could see, modern science has revealed that most of this liquid mystery remains largely uncatalogued by human endeavor. Today, estimates calculate that we have successfully mapped and studied less than 5% of the world's oceans. That means over 95% of life on Earth, the unseen megafauna, the alien geology, the untouched hydrothermal vents deeper than Everest is tall, remains a profound scientific guess. Think about it. Entire trenches like the Challenger Deep in the Mariana Trench remain hostile, crushing fortresses that defy easy exploration. It's a frontier far wilder and more mysterious than outer space itself, inviting us to ask, what incredible secrets are waiting in the deep today? Imagine what it's like down there. We're talking about environments that defy everything we consider normal life. The abyssal plains are realms of crushing pressure, absolute darkness, and near-freezing temperatures. At depths reaching 6 or even 8 miles, the water pressure could equal stacking 50 jumbo jets on a single swimmer. Your bones would collapse into kindling without specialized equipment. The lack of sunlight is so total it's often described as an eternal midnight, forcing life to adapt with bioluminescent magic. For much of history, these depths were simply blank spaces on the map, vast unknowns that terrified sailors and captivated scientists. It wasn't until pioneering deep-sea submersibles in the mid-20th century, like Alvin Asterisk, that we began to peek into this profound alien world. These conditions mean that any life there has evolved unique ways to regulate internal chemistry, often bypassing standard biological needs entirely. It's a hostile place by all accounts, yet teeming with complex, almost unbelievable ecosystems. Imagine trying to really understand our own planet, only to realize most of it is fundamentally unreachable. For millennia, the ocean remained this terrifyingly immense frontier, and deep-sea exploration wasn't something science accomplished easily. It was something that took massive leaps in engineering simply to begin. Until very recently, the crushing pressure and absolute darkness of the abyssal zone made comprehensive mapping virtually impossible outside the immediate coastline. Early attempts were groundbreaking, but often limited by fragile vessels or prohibitively shallow diving bells. It wasn't until the mid-20th century, with technological strides like advanced sonar technology and specialized submersibles, that humans could truly begin to peer into these deepest realms. Vehicles like those designed for deep-sea research finally gave us windows onto entirely new biospheres, revealing life forms unlike anything we had previously imagined. Suddenly, what was considered an impenetrable black void became a complex, vibrant ecosystem. These advancements didn't just change our technology, they fundamentally altered our definition of what's possible on Earth itself. Down in these crushing depths, sunlight is nothing more than a myth. Yet, life doesn't quit. Instead, it finds its own spectrum of light. This is the realm of bioluminescence, a chemical glow generated by living organisms themselves. Imagine a creature, perhaps a deep-sea squid, using that soft blue flare not just for illumination, but as a sophisticated lure or even a distraction to confuse predators trying to corner it. Far stranger still are the extremophiles, life forms found near hydrothermal vents, places where superheated, mineral-rich water spews out miles below Earth's surface. These unique ecosystems don't rely on photosynthesis. They sustain themselves through chemosynthesis, essentially eating the toxic chemicals bubbling up from the planet's crust. It challenges everything we thought we knew about biology. Life simply refuses to be confined by boundaries of light and energy. Every time a submersible like the asterisk Nautil dives deeper, it reminds us that Earth remains an immense biological library, filled with chapters we haven't even started reading yet. It's not just the continental shelves that keep secrets beneath the waves. The deepest trenches are powered by Earth's very inner workings. Massive geological processes, the slow dance of tectonic plates, are constantly ripping and reshaping our planet, creating environments unlike anything seen on dry land. When these colossal slabs grind against one another, they generate intense heat and incredible pressure anywhere from the Mariana Trench to the Mid-Atlantic Ridge. This unimaginable energy is responsible for hydrothermal vents, deep-sea oases that glow with chemical life rather than sunlight. These vents spew superheated, mineral-rich fluids, sometimes reaching over 400 degrees Fahrenheit, laden with chemicals like hydrogen sulfide and methane. For decades, scientists thought all oceanic life required photosynthesis, but these vent communities proved them wrong. They powered the first breakthroughs in biochemistry, proving that life can thrive purely on chemosynthesis. Imagine whole ecosystems built around geothermal energy, completely independent of surface sunshine. These hotspots fundamentally changed our understanding of biology, suggesting that perhaps life could even exist beneath the ice crusts of Jupiter or Saturn. It's easy to look at a satellite image of Earth and forget just how perilous this blue frontier truly is. To explore the deep ocean isn't like going up Mount Everest. It's entering an alien realm under crushing pressure, miles below the reach of sunlight. Consider the early days of submersible exploration, where pioneering figures often face not just technical failure, but outright catastrophic risk to life itself. Men like Jacques Cousteau built legends on thin wires and fragile metal shells, turning sheer survival into a scientific triumph. Today, modern missions still echo that bravery, sending highly trained individuals, academics, pilots, engineers, down depths where visibility is near zero. Think of the constant whirring noise of specialized deep-sea vehicles like the Nereus asterisk, monitoring every fluctuation in temperature and pressure. These explorers aren't just collecting specimens. They are battling isolation, time zones, and the immense psychological weight of being so far from home. Their personal dedication to turning curiosity into tangible knowledge is a breathtaking testament to human will. They send down robotic eyes capable of documenting life forms that have never known an atmosphere, pushing not just machines, but the very boundaries of what we believe is possible in nature. But this immense lack of exploration isn't just a scientific curiosity. It's an untapped financial vault. When we talk about resources, we're talking about extraordinary concentrations, from polymetallic nodules scattered across abyssal plains to hydrothermal vents spewing precious metals like copper, zinc, and rare earth elements. These depths hold vital components for the green energy transition, fueling everything from massive battery storage systems to advanced electric motors. Beyond the mineral haul lies a bioactive ocean pharmacy. Scientists are only beginning to understand the biochemical compounds harbored by deep-sea organisms, potential keys to revolutionary pharmaceuticals for diseases like cancer and arthritis. Furthermore, the sheer scope of the ocean's role in global climate regulation cannot be overstated. It acts as the planet's greatest carbon sink, absorbing colossal amounts of atmospheric CO2 over millennia. Understanding these systems isn't just research. It is basic survival science, a ticking time bomb linked directly to humanity's sustainable future. But this vastness isn't just unknowable. It is actively threatened by us, right now. Deep-sea mining, for example, aims to strip polymetallic nodules, rich in cobalt and nickel, from areas like the Clarion-Clipperton Zone, regions teeming with undiscovered life found near hydrothermal vents that process energy without sunlight. These proposed operations carry the risk of permanent deep ocean sediment plumes, smothering benthic ecosystems built over millennia. Compounding this industrial threat is the accelerating climate crisis, which drives not only ocean acidification, but also warming currents, fundamentally altering habitats and forcing species migration far faster than they can adapt. We simply cannot afford to treat the deep sea as a limitless resource dump or an ecological wastebasket. If we don't commit ourselves to international regulations, stronger protections than the current framework allows, we risk losing vital biological knowledge before humanity even knows what it was. The incredible biodiversity, which includes organisms unique to specific trenches and geysers, needs our immediate defense, not just for its own sake, but because understanding it could hold the keys to medicines we desperately need. It's a crucial race against time. Exploring these depths must happen in lockstep with protecting them from irreversible damage. The ocean is not just water, it is the planet's greatest library of life and raw materials. By recognizing its unexplored depths, we understand that our own future depends on protecting these silent, powerful realms. Next time you think about the depth below us, remember the 95%, a frontier waiting for humanity to finally open the book.